This is part 2 of a multi-part series from a guest lecture that Lily gave at the Hong Kong University of Science and Technology. When OpenAI first released GPT-3 in late 2022, it was a paradigm shift from the types of AI that has come before. In this part, we will talk about 4 key differences between the AI that we see today compared to what came the 10 years prior. Firstly, the technology changed from being usable for a single specific domain to being able to cross many domains. Secondly, we went from models that were primarily trying to learn from humans directly through supervised learning to being able to ingest unstructured data by themselves through a process of unsupervised learning. Thirdly, we went from needing to provide very specific input to the AI model to being able to input using natural language. In other words, previously we had to speak the language of machines, and now the machines speak in our language. Finally, in the previous paradigm, most of the models were reductive. It took an input of a certain size and gave us something smaller back. Now, they are able to generate. Let's step through each of them. The MMLU benchmark is a test that is frequently used to compare the capability of large language models against one another. It is a very good example of how models can span a huge variety of specialist domains. Back in 2020, the state-of-the-art was 28% accuracy on the MMLU. Given that MMLU are multiple choice questions with 4 answers to choose from, this was just barely better than random guessing. In January, Google released the Gemini Ultra, which delivered a 90% accuracy in the MMLU. To really appreciate what this means, let's have a look at some example MMLU questions. On the left side here is a question given to medical professionals. You can see that it describes the symptoms of a 63-year-old man who presented to the emergency department with leg pain and swelling, etc. To answer this question correctly, the AI has to choose answer B. On the right side is a question for professional accountants. It describes a complicated tax situation and asks what is the penalty that the person must pay for the underpayment of tax. Those are just 2 examples. The MMLU covers 57 subjects, including college-level biology, chemistry, physics, high school geography, history, international law, etc. Today, with these LLMs, one single model can span across many domains. This means that the need for each company to have to put together training data and train their own models is becoming less and less. Let's talk about the shift from supervised to unsupervised learning. This is a classic example of supervised learning. ImageNet is a database of 1.2 million images that humans have manually tagged with a label. There are 1,000 defined labels in this dataset, for example, dog, cat, hamburger. When you train the AI model, you have the ground truth label as being the one the humans tagged. When the model outputs an answer, you check the difference between the output and the correct answer. If the loss is big, then have to tweak the weights in the model until that loss gets smaller and smaller and converges. This is just a fun side project that I did to take the weights from a model trained on ImageNet images, freezing the weights other than the final few layers of the neural network and fine-tuning the model to recognize 50 of my favorite foods. By using transfer learning, which is like copy and pasting someone else's brain to serve as the starting point of your own, I was able to get this to work with only 2,000 tagged images, not millions. But even with techniques like transfer learning, models are growing bigger and bigger, to the point where relying on human-labeled structured data becomes a major bottleneck. GPT-3 has 175 BN parameters, and GPT-4 has 10x more than that just 1 year later. The bigger the models get, the more data they need to ingest to work well. These GPT models are first pre-trained by ingesting huge volumes of unstructured data using unsupervised learning techniques. By the end of the pre-training, the model knows how to complete sentences that you give it. To teach this model how to do tasks that we want it to do, e.g. answer questions like a chatbot, foundation model developers have to do some supervised fine-tuning using the same input-output data technique using a dataset put together by humans. You can see this labeled as SFT in the diagram. This is followed by some behavioral shaping called reinforcement learning with human feedback, or RLHF in short. Think of RLHF like training a dog where correct behaviors are reinforced with rewards, maybe a treat, and undesired behaviors are noted with no. If you go on Hugging Face, this is a giant repository of open source models and more. You will see that Meta has released numerous versions of Llama 2. The one that ends with 70B is one that has completed pre-training, ready for you to do the SFT and RLHF by yourself. The one that ends with Chat is the one that has completed the whole training pipeline. As an example of what data is used during unsupervised pre-training, The Common Crawl contains 250 billion web pages collected over 17 years. You might wonder how this kind of unstructured data is used for training. This example will give you some intuition for how unsupervised learning works. You can think of it like self-supervised learning. Think about when you are preparing for exams. You might cover up some part of the textbook to see if you can come up with the correct answer, and then lift your hand to compare your answer with the textbook. Here we call it masking. The model will mask the next word in the sentence and see if the AI model can correctly guess the next word. The difference between the prediction and the correct answer is used to further adjust the weights of the model until the loss is low and the model converges. This self-supervision technique doesn't only work for text, you can also do it with images. Here is one example where some pixels of the original image is deliberately obfuscated. The model's job is to correctly guess this missing pixels. The difference between the predicted image and the correct image is the loss. The point of training is to keep adjusting the weights of the model, so this loss becomes as low as it can be. Think about how you learn. Supervised learning is like sitting in a lecture, listening to your teacher. Unsupervised learning is like going to a library and reading lots of books by yourself. Reinforcement learning is like going out into the world where you learn the consequences of actions and decisions that you take. As an example of the power of reinforcement learning, we can look into AlphaGo. Google Deepmind developed AlphaGo Zero, which learned how to play the game of Go without looking at any past human experts play. It was just given the rules of the game. It played 5 million games by itself and was able to achieve superhuman capability. You can think of this as generating and using synthetic data for learning. Today, our AI is still mostly limited to very contained type of reinforcement learning. But when we have embodied AI who can see, touch, hear, they can explore the world and learn about the world. This can also happen inside simulated environments like games. Some people believe that reinforcement learning is key to artificial superhuman intelligence. What do we mean by fixed input schema? Let's have a look. Back in 2012, using AlexNet, we can input an image and the output is a class, such as dog or cat. The input image has to be in a very precise format, 227 by 227 pixels split into 3 matrices, red, green, and blue. It must be square. If your image is not square, you must crop it until it is exactly the input format that the AI requires. If you look at OpenAI's ChatGPT now, the input can be anything from a single sentence of 48 pages of text, 32,000 tokens. On the right side, you can see that Google's Gemini model was announced to have a context window of 1 million tokens, and it can take text, images, audio, all interleaved. This makes it much easier to use than the AI of 10 years ago. On this slide, you can see an example of a task in Google Gemini's technical paper. The prompt includes a hand-scribbled answer to a physics question by a student, including a hand-drawn graph and the workings. Gemini was asked to verify whether the student's response is correct. The input is an interleaved mix of typed text, written equations, and drawn graphs. Previously, if we wanted to teach AI to do a new task, we would have had to choose a suitable neural network architecture, put together a set of human-labeled data, and train a model. Now, all we need to do is to provide a few examples through the prompt. Zero-shot prompting means simply asking GPT to do the task without providing any worked examples. One-shot prompting means you provide one completed example with input and sample output to show the model what you want it to do. Few shots prompting means providing multiple worked examples. This is why the size of the context window is so important. Not only can you teach the model new tasks through the window, you can also feed it new data to draw from without needing to retrain. In a recent interview, Jensen Huang, the CEO of Nvidia, noted that regardless of whether you know how to code or not, everyone can now program computers, because computers speak our language. Finally, let's talk about what we mean by reductive. Before GPT and large language models came into vogue, most of the tasks that AI did for us involved putting in some input and then getting some smaller-sized output back. For example, in summarization, we put in long text and get out some shorter text. In sentiment analysis, we put in a sentence or a paragraph and we get out a number. For retrieval, we might put in a database of documents and get one relevant piece back. For object detection in an image, we feed in lots of pixels and we get back the XY coordinates of the bounding box of that object. Now with generative AI, we can put in a short prompt like this and get out a 1-minute long video. That significantly increases the range of tasks that AI can do for us. This example is from OpenAI's new release called Sora. Next up, Part 3 will talk about approaches and challenges to AI deployment in the workplace.